Hi everyone, in this video I'm gonna explain how to solve this problem. The problem has two parts. The first one is if we have a measure space and we have a measurable function, then we can utilize the measure mu to define a new measure, and also by utilizing the measurable function. So we're gonna check the axioms of the measure. And then in the second part, we're gonna show how to actually integrate the any function with respect to the new measure, and then how to connect the integral to the original measure. Okay, so the first part is easy. Let's recall the definition of the measure. So for a function to be a measure, we have to satisfy two properties. The first one is new empty would equal to 0. So let's notice the definition of the new A, which is just equal to mu of f inverse empty. So this one would be empty again, so we'll have new empty. As mu is a measure, so this one would be 0. And another property is if we have some disjoint measurable sets, then the union of those measurable sets would equal the summation of the measure of each set. Okay. And now notice we're working with the Borel measure, or the Borel sigma algebra. So then we're gonna take a bunch of Borel sets, and we're gonna check. So the EJs would essentially be in the Borel sigma algebra of R, which are some open sets or some intersection unions. So let's recall the Borel. So the sigma algebra of Borel sets is the smallest sigma algebra that contains all the open sets. So it might contain all the other set as well. Okay, then we're still gonna rely on the definition. So let's do it by union equals the mu of f inverse union of EJ, which is essentially just the inverse of the union of f inverse EJ. And still as mu is a measure, we can just by utilizing mu as a measure to get the result, which is equal to f inverse EJ. And this one would just be by definition would be the nu of EJ. Okay, so now we showed the nu is a measure. So let's do the second part. The second part is a bit not easy or not straightforward, because we have some Borel measurable functions, which are not necessarily to be simple, or which may not be nice. But recall that we can approximate any function by simple functions. So we're gonna utilize that to prove this part 2. So let's start with simple functions and then try to approximate any other functions by using the simple functions. Now before we actually do that, let's see so we have to show that this integral actually makes sense, which is essentially show that G composite with F is actually measurable. So then we recall the definition of for a function to be measurable. We have to satisfy some property. So let's check. So for this function to be measurable, then we have to show that if we take G of F inverse of some B, here B is Borel set, then it has to in the sigma algebra of F, as we can see, the G composite with F inverse B equals the G equals the F inverse G inverse B. So G inverse B is inside R, and this one is by the measurability of F would be in the sigma algebra of the original measure space. So now this function actually makes sense, and this integral actually makes sense. Then we can do the integration. We can do the simple functions first. So let G be equals to some summation of indicator functions times some constant. Then we have the G composite with F integrate with respect to d mu is actually summation of ci times indicator of bi. Here bi's are in the Borel set of R. So and the input of the function would be fx, or we can just write f d mu, and then we can pull out the summation and the constant, as the integrals are linear and we are dealing with finite terms. So then we ended up with this expression. Then we ask ourselves how to connect this one, this the measure of the new measure, then essentially the indicator of the function would equal the 1 if fx is in bi, and it would equals the 0 if fx is not in bi, which could help us to simplify the expression, because essentially we only care about where the function values doesn't vanish. So in that case, the expression would be just summation of a bunch of constants. And we also notice, so fx has to be in bi, so the indicator functions would just be how many values, or would just be the f inverse of bi, because if it's not inside bi, then the function value is 0, so we don't care about any values of 0. So we have that in mind. The indicator function would be just the measure of the set of bi, f inverse bi, and then it, by definition, it equals the mu bi, which equals the g d mu. So that's the case for simple functions. And if we have that, we can easily generalize the result to any other non-simple functions by choosing that by choosing a sequence of increasing simple functions. And let gx equals the limit of those simple functions. As we know, the simple functions are non-negative and we are having some increasing sequence. So it's pretty natural for us to use the MCT, the monotone convergence theorem. Which would give us the results. So essentially the integration of g d mu would be limit I goes to 0. We integrate the simple functions with respect to d nu, and as we've already shown, the result holds for simple functions, so it has to equal the limit I goes to 0 as I composite with f d mu x, or just d mu. And as those two so as those functions are also like increasing, because each si, so si plus 1 is greater than si plus is greater than si, so si plus 1 composite with f would be greater than si. So here we also have a sequence of increasing functions, so we can use the monotone convergence, MCT, again to put the limit inside of the integral. Then this would be just g, and g composite with f. Okay, so that's the solution of this problem.